So here's something worth thinking about as you settle in tonight. Right now, wherever you are, you're lying on what feels like perfectly solid, perfectly still ground. Maybe a bed, maybe a couch, maybe a pile of blankets on the floor. It doesn't matter. The point is, everything feels stable, motionless. The room isn't spinning. The floor isn't lurching. Gravity is pulling you gently downward into whatever surface you're resting on, and nothing about this moment suggests that anything dramatic is happening. It feels like the most peaceful, most stationary experience imaginable, and every single part of that feeling is a lie. Right now, the ground beneath you is spinning. The entire planet is rotating on its axis at roughly 1,000 miles per hour at the equator. That's faster than the speed of sound. And while it's doing that, it's also hurtling around the sun at about 67,000 miles per hour. And the sun itself is dragging the whole solar system around the center of the Milky Way at something like 500,000 miles per hour. And the galaxy itself is moving through the universe at a speed that depends on what you measure it against, but some estimates put it at over 1,000,000 miles per hour relative to the cosmic microwave background radiation. You are, at this exact moment, moving at a genuinely absurd speed through space, and you can't feel any of it. Not a thing. Think about that for a second. 1,000,000 miles per hour, and you feel nothing. Not a breeze, not a vibration, not the slightest hint that you're doing anything other than lying perfectly still. And that's the first confusing thing about Earth. Why can't you feel it? Why doesn't the rotation fling you off the surface like water off a spinning tennis ball? Why doesn't the wind scream at 1,000 miles per hour as the ground whips beneath the atmosphere? The answer is surprisingly simple, and it goes all the way back to Galileo. You can't feel constant motion. If you're in a car on a perfectly smooth highway, going a steady 60 miles per hour, and you close your eyes, you can't tell you're moving. You only feel changes in motion, acceleration, deceleration, turning. The Earth's rotation is remarkably steady, and you, the atmosphere, the oceans, everything on the surface has been spinning at the same rate for billions of years. You're all moving together. There's nothing to push against. No wind created by the rotation, because the air is spinning too. It's like sitting inside a car with the windows up. The air inside the car isn't blowing in your face because it's moving with you. Same principle, same physics, scaled up to an entire planet. Now, that's not quite the whole story. Because the Earth is spinning, there is a slight effect. You do weigh a tiny bit less at the equator than at the poles. The centrifugal tendency of the rotation pushes you outward, away from the axis, and that works against gravity just a little. If you weigh 150 pounds at the North Pole, you'd weigh about half a pound less at the equator. Not enough to notice on a bathroom scale, but enough for precision instruments to detect. And here's a fun wrinkle. Because of that same rotational bulge, the Earth isn't a perfect sphere. It's an oblate spheroid, slightly squashed at the poles and slightly fatter at the equator. The equatorial diameter is about 27 miles wider than the polar diameter. Not a huge difference on a planet nearly 8,000 miles across, but it's there. The Earth is, technically, a bit pudgy around the middle. But let's go back to something more fundamental. The shape of the Earth. The fact that it's round at all. Because for most of human history, that wasn't obvious. If you walk outside and look at the horizon, the world looks flat. It looks like a vast, level plain stretching out in every direction. And most ancient civilizations assumed exactly that. There's nothing stupid about it. The curvature of the Earth is so gentle that you can't perceive it at ground level. You'd need to see about 3 miles in every direction from a height of about 6 feet before the curvature would even start to become noticeable, and even then, only if you had perfectly clear sight lines and knew exactly what to look for. But the ancient Greeks figured it out. Several of them, actually, working from different lines of evidence. Aristotle, around 350 BCE, pointed out that during a lunar eclipse, when the Earth passes between the Sun and the Moon, the shadow Earth casts on the Moon is always circular, no matter what angle the eclipse occurs from. The only shape that always casts a circular shadow, from any direction, is a sphere. That's a beautifully simple geometric argument, and it's completely correct. He also noted that as you travel north or south, different stars become visible above the horizon, which wouldn't happen if the Earth were flat. But the really stunning achievement came about a century later, from a man named Eratosthenes, who was the chief librarian at the Great Library of Alexandria in Egypt. Around 240 BCE, Eratosthenes heard that in the city of Syene, far to the south, that's modern-day Aswan, on the summer solstice, the sun passed directly overhead at noon. Perfectly, directly overhead. You could tell because a vertical stick cast no shadow, and sunlight shone straight down to the bottom of a deep well. But in Alexandria, on that same day, at that same time, a vertical stick did cast a shadow. The sun wasn't quite directly overhead. It was offset by about 7 degrees from vertical. Now, here's where Eratosthenes did something clever. He reasoned that if the Earth were flat, the sun would be at the same angle everywhere at the same time. The fact that the angle was different in 2 different cities meant the surface of the Earth was curved, and the difference in angle, about 7 degrees, told him how much the surface curved between those 2 cities. 7 degrees is roughly 1/50th of a full circle. So the distance between Alexandria and Syene was roughly 1/50th of the Earth's total circumference. He estimated the distance between the 2 cities at about 5,000 stadia. There's some debate about exactly how long an Egyptian stadion was, but most estimates put it at roughly 500 feet. Work it out, and Eratosthenes arrived at a circumference for the Earth of about 25,000 miles. The actual value is about 24,901 miles. He was off by less than 2%. In 240 BCE, with a stick, a well, and some geometry. That's one of the most impressive measurements in the history of science. So the Greeks knew the Earth was round. They even had a decent estimate of its size. But there was another question lurking beneath that one, a much harder question that would take more than 2,000 years to answer. How old is the Earth? And this is where the story gets really interesting, because the history of trying to figure out the age of the planet is a story full of wrong answers, bitter arguments, and one quiet, stubborn scientist who was right when everyone was pushing back. For most of Western history, the answer came from Scripture. In the 17th century, an Irish archbishop named James Ussher famously calculated, by working backward through the genealogies and chronologies in the Bible, that the Earth was created on the evening before October 23rd, 4004 BCE. That gave the Earth an age of about 6,000 years. And while that might sound naive now, it was a serious scholarly effort at the time, and many people, including Isaac Newton, worked on similar calculations. 6,000 years was the accepted answer for a very long time. But by the late 18th and early 19th centuries, geologists were starting to realize that 6,000 years wasn't nearly enough. James Hutton, a Scottish farmer and geologist, looked at rock formations in Scotland, layers upon layers of sediment, deposited and eroded and deposited again, and concluded that the Earth had to be inconceivably old. He wrote, in 1788, one of the most famous lines in the history of geology, "We find no vestige of a beginning, no prospect of an end." Hutton saw that the processes shaping the Earth, erosion, sedimentation, volcanic activity, were slow, gradual, and ongoing. And if you calculated how long those processes would take to produce the rock formations he could see with his own eyes, you needed not thousands, but millions or hundreds of millions of years, at minimum. Charles Lyell, another Scotsman, built on Hutton's work in the 1830s and popularized the idea of deep time, the notion that the Earth is old, on a scale that the human mind can barely grasp. Darwin relied heavily on Lyell's geology because his theory of evolution by natural selection required enormous stretches of time for the slow accumulation of small changes to produce the diversity of life. Deep time wasn't just a geological curiosity. It was the stage on which the entire drama of life on Earth played out. But here's where things got contentious. In the 1860s, one of the most prominent physicists in the world entered the debate and said everyone was wrong. His name was William Thomson, later Lord Kelvin, and he was brilliant, formidable, and absolutely certain. Kelvin calculated the age of the Earth using physics, specifically thermodynamics. He treated the Earth as a body that started out molten and has been cooling ever since. And he calculated how long it would take for the surface to cool to its current temperature. His answer: somewhere between 20 million and 400 million years, with his best estimate settling around 100 million. And for the geologists and biologists who needed hundreds of millions or even billions of years, this was a problem. Kelvin was one of the most respected scientists alive. You didn't just wave away his calculations. And here's the thing. Kelvin's physics was perfectly correct, given what he knew. His math was right. His thermodynamics was impeccable. But he was missing something nobody knew about yet, because it hadn't been discovered. Radioactivity. In 1896, Henri Becquerel discovered that uranium emits radiation spontaneously, and within a few years, Marie and Pierre Curie and others had begun to understand what was happening. Atoms of certain elements were unstable and were decaying, releasing energy in the process. And that energy, that radioactive decay happening throughout the Earth's interior, was generating heat. Kelvin's calculation assumed the Earth had no internal heat source and was simply cooling from its original molten state. But radioactive decay provided a continuous supply of heat from within. That extra heat source meant the Earth could maintain its current temperature for far, far longer than Kelvin had estimated. His answer was wrong, not because his physics was bad, but because the universe had a trick he didn't know about. And radioactivity didn't just invalidate Kelvin's estimate. It provided the tool that would eventually give us the right answer. Because radioactive decay happens at a known, constant rate. Each radioactive isotope has a half-life, the time it takes for half of any sample to decay. Uranium-238, for example, has a half-life of about 4.47 billion years. If you can measure how much of a radioactive isotope is left in a rock sample and how much of its decay product has accumulated, you can calculate how long that rock has been sitting there. It's like finding a candle that burns at a known rate and measuring how much wax is left. The shorter the candle, the longer it's been burning. Ernest Rutherford, the same physicist who would later discover the atomic nucleus, was one of the first to realize that radioactivity offered a clock for dating rocks. In 1904, he gave a lecture at the Royal Institution in London on the topic, and Lord Kelvin himself was in the audience. Rutherford later recalled noticing Kelvin in the front row, his eyes fixed and seemingly hostile, and feeling a mounting dread as he realized his argument was about to demolish the old man's life's work on the age of the Earth. Rutherford diplomatically noted that Kelvin had said his estimate was valid, provided no new source of heat was discovered, and radioactivity was exactly such a source. Kelvin, by some accounts, was not entirely appeased, but the science was clear. The Earth was far, far older than Kelvin had calculated. The person who finally nailed down the age of the Earth with precision was a geochemist named Claire Cameron Patterson, and his story is one of the great unsung tales in science. In the 1940s and 1950s, Patterson set out to determine the age of the Earth by measuring lead isotope ratios in meteorites. The idea was that meteorites formed at the same time as the Earth from the same cloud of dust and gas, so their age would be the Earth's age. But there was a problem, a maddening, baffling problem. Every sample Patterson analyzed was contaminated with lead. Not just a little, a lot. Lead was everywhere, in his instruments, in his reagents, in the dust in his lab. It was so pervasive that he couldn't get a clean measurement. Patterson spent years fighting contamination. He built one of the first ultra-clean laboratories in the world, pioneering techniques for removing trace contaminants that would later become standard in analytical chemistry. He traced the contamination to its source and discovered something alarming. The lead wasn't natural background. Much of it was coming from tetraethyl lead, the additive used in gasoline to prevent engine knock. Lead from car exhaust was settling on everything, blanketing the entire surface of the planet in a thin film of toxic metal. Patterson's crusade to get lead removed from gasoline would become one of the most important public health campaigns of the 20th century. But that's a story for another time. The point is, after years of painstaking work, Patterson got his clean measurements. In 1956, he published his result. The age of the Earth, 4.55 billion years, plus or minus 70 million. The current best estimate, using multiple independent methods and many more samples, is 4.54 billion years. Patterson was essentially dead on. 4.5 billion years. Think about that number for a second. 4,500 million years. That number is genuinely impossible for the human mind to comprehend. We can say it, we can write it down, but we can't really feel it, not the way we can feel an hour or a week or even a century. It's a number so large that all our attempts to make it tangible are really just different flavors of inadequacy. But let's try one anyway. If you compressed that into a single 24-hour clock, with midnight representing the formation of the Earth, and the current moment being midnight again, all of recorded human history, every empire, every war, every book ever written, every person who ever lived, would fit into the last fraction of the last second before midnight. We are a blink, less than a blink, and the Earth has been here, spinning and churning and transforming, for an almost incomprehensible span of time before us. And to really appreciate what that number means, think about how the Earth formed in the first place. Because the planet didn't just appear. It was built, slowly, violently, out of the debris left over from the birth of the Sun. About 4.6 billion years ago, a vast cloud of gas and dust, mostly hydrogen and helium, but laced with heavier elements forged in previous generations of stars, began to collapse under its own gravity. As it collapsed, it spun faster, the way an ice skater spins faster when they pull their arms in. The spinning flattened the cloud into a disk, with a dense, hot ball forming at the center that would become the Sun. And in that disk, in the swirling plain of gas and dust, orbiting the young Sun, something remarkable began to happen. Tiny grains of dust and ice began sticking together, not through gravity at first. They were too small for that. Through static electricity, essentially, and through simple physical contact. Grains stuck to grains and became pebbles. Pebbles accumulated into rocks. Rocks grew into boulders. And once the accumulations got large enough, maybe a kilometer across, their own gravity started pulling in more material, and the growth accelerated. These growing bodies are called planetesimals. and the process of building them up through collisions and gravitational attraction is called accretion. It was chaotic, violent. Planetesimals collided with each other constantly, sometimes shattering, sometimes merging. The inner solar system was a demolition derby, but gradually, a few bodies grew large enough to dominate their orbital neighborhood, sweeping up or ejecting the smaller debris. These protoplanets grew rapidly, heated by the energy of all those impacts and by the radioactive decay of elements like aluminum-26 and iron-60. The young Earth was probably largely molten for much of its early history, a seething ball of magma, with no solid surface, no atmosphere to speak of, bombarded relentlessly by leftover debris. It was, to put it mildly, not a nice place. Scientists call this period the Hadean, after Hades, the Greek underworld, and that name is well chosen. But the bombardment eventually slowed, the surface cooled, a crust formed, and during all that time, things have been happening, dramatic things. The interior of the Earth has been churning. Continents have been drifting. Mountains have been rising and eroding away. Oceans have opened and closed. The atmosphere has been completely reinvented more than once, and the engine driving all of it, the force powering nearly every geological process you've ever heard of, sits thousands of miles beneath your feet right now, hot and restless, and utterly invisible. Which raises a question that seems almost absurdly basic, the kind of thing you'd think we'd have figured out easily. What, exactly, is inside the Earth? What's down there? And here's the confusing part. Nobody has ever seen it. Nobody has ever been there. The deepest hole humans have ever drilled barely scratched the surface. And yet we know what's down there, in remarkable detail. How? That's a story that involves earthquakes, a woman who was told she couldn't be a scientist, and a discovery that changed everything we thought we knew about the planet's core. The deepest hole ever drilled by humans is the Kola Superdeep Borehole on the Kola Peninsula in northwestern Russia, near the Norwegian border. The Soviets started drilling it in 1970, and they kept going for over 20 years, pushing deeper and deeper into the Earth's crust. By 1989, they had reached a depth of about 7.6 miles, roughly 12 kilometers. That's deep by human standards. If you could somehow stand at the bottom and look up, you'd be farther below the surface than a commercial airliner is above it. But in geological terms, it's nothing. The Earth's radius is about 3,959 miles. The Kola borehole penetrated about 0.2% of the way to the center. It's like poking a pin into the skin of an apple. You haven't even gotten through the peel. And they had to stop, not because of any political decision, but because of heat. At the bottom of the borehole, the temperature was about 356 degrees Fahrenheit, far higher than they'd expected. The rock at that depth was behaving almost plastically, flowing like very thick putty, rather than cracking and fracturing, the way rock does near the surface. The drill bits couldn't handle it. The engineering had reached its limit. So if we can't drill to the center of the Earth, how do we know what's there? The answer is one of the most elegant solutions in all of science, and it relies on something that happens naturally, violently, and unpredictably all over the planet: earthquakes. When a major earthquake occurs, it sends seismic waves radiating outward through the Earth's interior in all directions, like ripples from a stone dropped into a pond. But these aren't simple ripples. There are different types of seismic waves, and they behave differently depending on what kind of material they're passing through. The two main types are P waves and S waves. P waves, or primary waves, are compressional waves. They push and pull the rock in the direction they're traveling, like a slinky being compressed and stretched. S waves, or secondary waves, are shear waves. They move the rock side to side, perpendicular to their direction of travel, like shaking a rope. Here's the critical difference. P waves can travel through anything: solid rock, liquid, even gas. But S waves can only travel through solids. They cannot pass through liquid. They just stop. And this simple fact, this difference in how two types of waves behave in liquids versus solids, is the key that unlocked the entire interior of the planet. In 1906, a British geologist named Richard Dixon Oldham was studying records from a major earthquake, and he noticed something strange. When he plotted where seismic waves were detected around the world, there was a zone on the far side of the Earth from the earthquake where S waves simply didn't arrive. They vanished. P waves showed up, but S waves were missing. Oldham realized that there must be something inside the Earth that S waves couldn't pass through, something liquid. There had to be a liquid layer deep inside the planet. That was the discovery of the Earth's liquid outer core, and it was made not by drilling or digging, but by listening, by paying attention to what wasn't there. But the story gets even more remarkable. In 1936, a Danish seismologist named Inge Lehmann was studying seismograms from earthquakes in New Zealand and noticed something that the existing models couldn't explain. There were faint P-wave arrivals in places where the models predicted nothing should appear, in the shadow zone, where the liquid core should have bent all the waves away. Lehmann realized that these unexpected arrivals could be explained if there was something inside the liquid core, a solid inner core, that was reflecting and refracting the P waves back into the shadow zone. She published her findings in a paper with one of the most understated titles in scientific history. It was called simply P. That's it. The letter P with a prime symbol. Inside that unassuming paper was the discovery that the Earth has a solid inner core nested inside a liquid outer core, like a ball bearing floating inside a sphere of molten metal. And here's the thing about Inge Lehmann that makes her story even more striking. She was working in an era when women were routinely excluded from science. She studied at the University of Copenhagen in the early 1900s, one of very few women in the physics department. She later worked at the Danish Geodetic Institute, doing meticulous work analyzing seismograms at a time when seismology was considered a backwater of geology. Her colleagues, mostly men, had looked at the same data and missed what she saw. She was rigorous, patient, and right. She lived to be 104 years old, and near the end of her life, she was finally recognized as one of the most important seismologists in history. But for decades, her contribution was underappreciated. The solid inner core of the Earth, this fundamental feature of the planet you live on, was discovered by a woman who had to fight for the right to do science at all. So, thanks to seismology, here's what we know about the inside of the Earth. Picture it, in layers, like an onion. On the outside, there's the crust, the thin, solid shell you're lying on right now. Under the oceans, it's only about 3 to 5 miles thick. Under the continents, it's thicker, 20 to 40 miles. Sometimes more under mountain ranges. Either way, the crust is incredibly thin compared to the whole Earth. If the Earth were an apple, the crust would be thinner than the apple's skin. Below the crust is the mantle, and this is where things get confusing, because the mantle is not what most people think it is. It's not a sea of magma. It's not liquid. The mantle is solid rock. It's hot. Temperatures range from about 1,800 degrees Fahrenheit near the top to over 6,700 degrees near the bottom, but it's under so much pressure that it stays solid. However, and this is the key, on geological timescales, over millions of years, the mantle flows. It behaves like an incredibly viscous fluid. Think of it like glass. Glass is technically a solid, but over very long timescales, it can deform and flow. The mantle does the same thing, only much more dramatically. Hot rock from deep in the mantle rises slowly toward the surface because it's less dense. Cooler rock near the top sinks because it's denser. This creates enormous, slow convection currents, cells of circulating rock that move at roughly the speed your fingernails grow, a few centimeters per year. And these convection currents, these sluggish rivers of solid rock creeping through the deep earth, are one of the main forces driving everything that happens on the surface. Every earthquake, every volcano, every mountain range, every ocean basin, all of it, powered by heat from below, driving the slow, relentless churning of the mantle. Below the mantle, starting about 1,800 miles down, is the outer core. This is genuine liquid, not liquid rock, but liquid metal, mostly iron, with some nickel and lighter elements mixed in. It's blisteringly hot, somewhere between 7,200 and 9,000 degrees Fahrenheit, well above the melting point of iron, even at those pressures. And because it's liquid metal, it can flow and circulate, and those currents of liquid iron are doing something absolutely extraordinary, something we'll come back to later, because it's one of the most important and most confusing things about our planet. And at the very center, there's the inner core. Solid iron, mostly. About 760 miles in radius, roughly the size of the moon. It's even hotter than the outer core. Current estimates put it at around 9,800 degrees Fahrenheit, which is roughly the temperature of the surface of the sun. So why is it solid when the outer core, which is slightly cooler, is liquid? Pressure. The pressure at the center of the Earth is so enormous, about 3.6 million times atmospheric pressure, that it forces the iron atoms into a solid crystalline structure despite the insane temperatures. The inner core is a ball of solid iron, almost as hot as the surface of the sun, held together by the sheer weight of the entire planet, pressing in on it from every direction. And here's something genuinely surprising. The inner core is growing, very slowly. As the Earth gradually cools over billions of years, the outer core is slowly crystallizing onto the inner core, adding to it, making it bigger. This process releases latent heat, which helps power the convection in the outer core, which in turn generates. But we'll get to that. Because right now, I want to talk about what all this internal heat and all this deep earth churning actually does on the surface. Because the consequences are some of the most dramatic, most violent, and most beautiful phenomena on the planet. And the story of how we figured out the connection, the story of how we realized that the continents themselves are moving, drifting across the face of the Earth, like giant stone rafts on a sea of slowly flowing rock, is one of the most fascinating tales in all of science. It's a story about a man who was right about one of the biggest ideas in the history of geology, and who was mocked and dismissed and ignored for it, and who died in the ice before the world came around. His name was Alfred Wegener, and his idea was continental drift. Wegener wasn't a geologist. That was part of the problem. He was a German meteorologist and polar explorer, born in Berlin in 1880. He studied astronomy and then shifted to meteorology, and he was genuinely passionate about the atmosphere and the Arctic. He set records for the longest continuous balloon flight in 1906, staying aloft for over 52 hours. He participated in multiple expeditions to Greenland. He was tough, curious, and inclined to think big, interdisciplinary thoughts. The kind of scientist who didn't respect the boundaries between fields because he didn't see the point of them. And in 1910, something caught his eye. He was looking at a world map, just a regular map, the kind you'd find in an atlas. And he noticed something that many people before him had noticed, but nobody had taken seriously. The coastlines of South America and Africa fit together, not roughly, not vaguely. The eastern bulge of Brazil tucks into the Gulf of Guinea on Africa's west coast, like two puzzle pieces designed to interlock. It's striking enough that you can see it yourself on any map, and people had been commenting on it for centuries. The Flemish cartographer Abraham Ortelius noted the similarity as early as 1596, but everyone assumed it was a coincidence. Continents don't move. They're continents. They just sit there. Wegener didn't think it was a coincidence. He started digging, and the more he looked, the more evidence he found. It wasn't just the coastlines. The rock formations on either side of the Atlantic matched up. There were mountain ranges in eastern Brazil that were geologically identical to mountain ranges in West Africa, as if they'd once been part of the same chain and had been pulled apart. There were deposits of glacial till, rubble left behind by ancient glaciers, scattered across South America, Africa, India, and Australia, in places that are now tropical. If those continents had once been joined and positioned near the South Pole, the glacial deposits made perfect sense. If they'd always been where they are now, you'd have to explain why glaciers had carved through the Sahara. And then there were the fossils. This was some of the most compelling evidence. A small freshwater reptile called Mesosaurus had been found in both eastern South America and western Africa, and nowhere else on Earth. Mesosaurus was a freshwater creature. It couldn't have crossed the Atlantic Ocean. If the continents had always been separated by thousands of miles of open sea, how did the same animal end up on both sides? The same was true of Glossopteris, a distinctive fern whose fossils appeared on every southern continent, including Antarctica. The conventional explanation was land bridges, thin strips of land connecting the continents that had since sunk beneath the ocean. But nobody could explain the mechanism for how vast land bridges would rise and then conveniently disappear without leaving a trace. In 1912, Wegener presented his theory. He proposed that all the continents had once been joined in a single supercontinent, which he later called Pangaea, from the Greek for all lands. And over hundreds of millions of years, this supercontinent had broken apart, and the fragments had drifted to their current positions. He compiled an enormous amount of evidence, geological, paleontological, climatological, and published it in a book in 1915 called The Origin of Continents and Oceans. The reaction from the geological establishment was devastating. They dismissed him, mocked him in some cases. The criticisms were partly scientific and partly personal. The scientific objection was straightforward and, honestly, fair. Wegener couldn't explain how the continents moved. He suggested that the continents somehow plowed through the ocean floor, driven by centrifugal forces from the Earth's rotation and tidal forces from the Moon. And geophysicists immediately showed that those forces were far too weak, by many orders of magnitude, to push continents through solid rock. It would be like suggesting that a ship moves through the ocean because of the breeze from a butterfly's wings. The math just didn't work, and the personal attacks were vicious. Many geologists resented an outsider, a meteorologist for heaven's sake, telling them how their own field worked. The president of the American Philosophical Society called Wegener's theory utter damned rot. A prominent British geologist sniffed that Wegener's method wasn't scientific, but was instead the type of reasoning that appeals to the subjective mind. The rejection was nearly universal in the English-speaking world, though Wegener had somewhat more support among European geologists. Wegener continued to revise and expand his book through several editions, adding more evidence, refining his arguments. But the mechanism problem haunted him. He knew the continents had moved. The evidence was overwhelming, but he couldn't explain how, and without a mechanism, the geologists wouldn't listen. And in November 1930, during his third expedition to Greenland, Wegener died. He was 50 years old. He'd set out on a dog sled journey to resupply a remote inland weather station, succeeded in reaching it, and then headed back toward the coast. He never made it. His body was found the following spring, buried in the ice, carefully wrapped in his sleeping bag by his companion, who had also perished on the return journey. He was buried right there, in the Greenland ice sheet, and as the ice flows slowly toward the sea, his grave has been drifting westward ever since, at about 0.5 meter per year. He's still moving. The man who said continents drift is still drifting. And for the next 30 years, continental drift was mostly dead as a scientific idea. A few geologists kept the flame alive, but the mainstream consensus was that Wegener had been wrong, or at best, wildly speculative. The continents were fixed. The Earth's surface was stable. Case closed. Except it wasn't, because deep beneath the Atlantic Ocean, there was evidence that would blow the case wide open, and the person who first mapped it was a woman who wasn't allowed on the research ships that collected the data. Her name was Marie Tharp, and she saw what the ocean floor actually looked like before almost anyone else on Earth. Tharp was born in Michigan in 1920. Her father was a soil surveyor for the U.S. Department of Agriculture, and she grew up making maps. Literally, she'd go along on her father's fieldwork as a child and help draft terrain maps. She studied geology at the University of Michigan, one of the few places that admitted women to its geology program, partly because so many men were off fighting in World War II. After the war, she went to work at Columbia University's Lamont Geological Observatory, under the oceanographer Maurice Ewing. But there was a problem. Women were not allowed on the research vessels. Tharp couldn't go to sea. So while the male scientists went out on ships and collected sonar data from the ocean floor, Tharp stayed on land and did the painstaking work of turning that data into maps. And what she found was extraordinary. Working with enormous volumes of sonar depth readings, Tharp began plotting the topography of the Atlantic Ocean floor, and what emerged wasn't the flat, featureless plain that most people imagined. Running right down the middle of the Atlantic, like a seam on a baseball, was a massive underwater mountain range, the Mid-Atlantic Ridge. It stretched from Iceland to the southern tip of Africa, thousands of miles long, with peaks rising over a mile above the surrounding ocean floor. And right along the crest of that ridge was a deep valley, a rift, running the entire length. Tharp recognized what that rift valley meant. It looked exactly like what you'd expect if the ocean floor were being pulled apart, if the Earth's crust was splitting along that line, and new material was welling up from below to fill the gap. She mentioned this to her colleague Bruce Heason, and his initial reaction was dismissive. He told her it sounded like girl talk. He meant she was being fanciful, unscientific. She pushed back. The data was the data. And then something clicked. Around the same time, in the late 1950s and early 1960s, a Princeton geologist named Harry Hess was developing an idea he called, with deliberate understatement, geopoetry. Hess proposed that the ocean floor wasn't permanent. New crust was being created at mid-ocean ridges, where hot mantle material rose to the surface, solidified, and spread outward on both sides, like a slow conveyor belt. The continents weren't plowing through the ocean floor, as Wegener had proposed. They were riding on it. The ocean floor was the conveyor belt, and the continents were passengers. This was the mechanism that Wegener had been missing. The continents didn't need to push through solid rock. They were being carried along by the spreading of the ocean floor itself, driven by convection currents deep in the mantle. The energy source wasn't the feeble forces Wegener had suggested. It was the enormous heat engine of the Earth's interior, powered by radioactive decay and primordial heat left over from the planet's formation. The same heat that had invalidated Lord Kelvin's age estimate was now explaining how continents move. And the confirmation came from an unexpected place: magnetism. In the early 1960s, researchers discovered that the ocean floor near mid-ocean ridges showed a striking pattern of magnetic stripes. The Earth's magnetic field, as we'll talk about more later, occasionally reverses. North becomes south, and south becomes north. When new ocean floor forms at a ridge, the iron-rich minerals in the cooling rock align themselves with the Earth's magnetic field at that moment, like tiny compass needles frozen in place. As the field reverses, the next batch of new rock records the opposite polarity, and as the seafloor spreads outward, it creates a symmetric pattern of magnetic stripes on either side of the ridge. Normal polarity, reversed polarity, normal, reversed, like a barcode stamped into the ocean floor. The pattern is identical on both sides of the ridge because both sides were formed at the same point and then carried outward in opposite directions. It was the smoking gun. The ocean floor was spreading, and it was recording the history of the Earth's magnetic field as it did. By the late 1960s, all of this evidence had coalesced into the theory of plate tectonics, one of the greatest unifying theories in the history of science. The Earth's surface is divided into about 15 major plates and several smaller ones, and these plates are in constant slow motion, riding on the convecting mantle beneath. Where plates pull apart, at divergent boundaries, new crust forms. That's what's happening at the mid-Atlantic ridge. Where plates collide, at convergent boundaries, one plate dives beneath the other in a process called subduction, plunging back down into the mantle, where it melts and is recycled. Where plates slide past each other laterally, at transform boundaries, you get faults like the San Andreas Fault in California. And this framework, this single, elegant idea, explains an astonishing number of things. It explains why earthquakes happen where they do. Plot every earthquake on a map, and they trace out the boundaries of the plates, like connect the dots drawing of the plate edges. It explains why volcanoes cluster in certain places. The famous Ring of Fire around the Pacific Ocean sits along a ring of subduction zones where oceanic plates are diving beneath continental plates. It explains why mountain ranges form. The Himalayas are rising because the Indian plate is colliding with the Eurasian plate, crumpling the crust upward like two cars in a slow-motion head-on collision. That collision started about 50 million years ago, and it's still happening. The Himalayas are still rising, at a rate of about 5 millimeters per year. Everest is getting taller while you sleep. And plate tectonics doesn't just explain where mountains are, it explains volcanoes. And volcanoes are, in a way, the most visceral reminder that the earth beneath your feet is alive, that there is an engine running down there, hot and restless and occasionally violent. Most volcanoes occur at plate boundaries, and the majority of them ring the Pacific Ocean in a horseshoe-shaped arc called the Ring of Fire. This ring traces the boundaries where the Pacific Plate and several smaller oceanic plates are being subducted, diving beneath the continental plates that surround the Pacific Basin. When an oceanic plate subducts, it carries water-rich sediments and hydrated rock down into the mantle. That water lowers the melting point of the surrounding mantle rock, causing it to partially melt and produce magma. The magma, being less dense than the surrounding rock, rises toward the surface, pooling in chambers beneath the crust, until pressure builds to the point where it erupts. That's why the west coast of South America has the Andes, studded with volcanoes. That's why Japan, Indonesia, and the Philippines are among the most volcanically active places on Earth. That's why the Pacific Northwest has Mount Rainier and Mount St. Helens. And some volcanic eruptions are so massive, so catastrophic, that they alter the climate of the entire planet. In 1815, Mount Tambora in Indonesia erupted in what is considered the largest volcanic eruption in recorded human history. It ejected roughly 36 cubic miles of material into the atmosphere, an almost inconceivable volume. The sulfur dioxide it injected into the stratosphere formed a veil of sulfuric acid droplets that reflected sunlight back into space, cooling the entire planet. The following year, 1816, became known as the year without a summer. Crops failed across Europe and North America. There were frosts in June in New England. Famine spread. In Switzerland, the dreary weather kept a group of writers trapped indoors at Lake Geneva, and one of them, Mary Shelley, just 18 years old, spent the time writing a ghost story. That story became Frankenstein. A volcano in Indonesia inspired one of the most famous novels in the English language. But even Tambora was modest compared to what the geological record shows us. Supervolcanoes, volcanic systems capable of eruptions hundreds or thousands of times larger than anything in recorded history, have shaped the Earth in profound ways. About 74,000 years ago, the Toba supervolcano in Sumatra erupted in one of the largest volcanic events of the last few million years. Some researchers have hypothesized that the resulting volcanic winter, years of reduced sunlight and plummeting temperatures, may have driven the human population down to as few as a few thousand breeding individuals. This is called the Toba bottleneck hypothesis, and while it's controversial, some genetic evidence supports it, other archaeological evidence doesn't. The eruption itself was undeniably enormous, and there's a supervolcano sitting right now beneath Yellowstone National Park. The Yellowstone hotspot has produced 3 massive eruptions in the last 2.1 million years, the most recent about 640,000 years ago. The caldera, the collapsed remnant of that last eruption, is about 34 miles by 45 miles. The geysers and hot springs that make Yellowstone famous are powered by the same magma system. Is it going to erupt again? Almost certainly, on a geological timescale. Is it going to erupt anytime soon? Almost certainly not. The geological record suggests intervals of hundreds of thousands of years between major eruptions, and current monitoring shows no signs of an imminent catastrophic event. But the fact that it's there, simmering quietly beneath the bison and the tourists, is a reminder that the Earth operates on time scales and energy scales that dwarf anything in human experience. And here's what's genuinely amazing about all of this. Wegener was right. He was right about almost everything. The continents were joined. They did drift apart. The evidence he collected was solid. He was right, and the scientific establishment rejected him, not because his evidence was bad, but because he couldn't explain the mechanism, and because he was an outsider. It took another 35 years for the mechanism to be found, and when it was, it vindicated nearly everything Wegener had proposed. He just didn't live to see it. Now, plate tectonics gives us a framework for understanding earthquakes, but that doesn't make earthquakes any less terrifying or any less confusing when you actually try to understand what happens during one. Because an earthquake isn't just the ground shaking, it's a sudden release of energy that's been building up for years, decades, sometimes centuries, enormous amounts of energy stored in deformed rock, like a spring being slowly compressed until it finally snaps. The technical term is elastic rebound. Imagine pressing your hands flat together and then trying to slide one forward while pressing hard. The friction holds them in place, but you're still pushing. The stress builds, and at some point the friction fails, and your hands suddenly slip past each other. That snap, that sudden release, is what an earthquake is, scaled up to the level of entire continents. The San Andreas Fault, which runs roughly 800 miles through California, is a transform boundary where the Pacific Plate and the North American Plate are sliding past each other. The Pacific Plate is moving northwest relative to the North American Plate at about 1.5 inches per year. That sounds glacially slow, and it is. But the plates aren't sliding smoothly. They're locked together by friction along most of the fault, building up stress year after year. And when the stress finally overcomes the friction and the fault ruptures, all that stored energy gets released in seconds. The result can be catastrophic. On April 18, 1906, at 5:12 in the morning, the northern section of the San Andreas Fault ruptured along a stretch of nearly 300 miles. The ground shifted by as much as 20 feet in some places. In San Francisco, the shaking lasted about 45 seconds to a minute, but those seconds destroyed most of the city. Buildings collapsed, gas mains ruptured, and fires broke out across the city, burning for 3 days because the earthquake had also broken the water mains, leaving firefighters with no water. Roughly 3,000 people died, and more than half the city's population, of about 400,000, was left homeless. It remains one of the worst natural disasters in American history. And the thing about earthquakes that makes them so frightening, so deeply confusing from a human perspective, is that we cannot predict them, not really. We know where they're likely to happen, along plate boundaries, along known faults. We know that stress is accumulating. We know that eventually it will be released, but we cannot say when, not within a year, not within a decade. The physics of fault rupture is chaotic in the mathematical sense. Tiny differences in conditions lead to vastly different outcomes. You can't measure all the relevant variables with enough precision to make a useful prediction. After more than a century of seismology, with thousands of sensors monitoring faults around the world in real time, we still cannot tell you when the next big earthquake will hit. We can tell you where, roughly. We can tell you how big it might be, but not when. The 2011 Tohoku earthquake in Japan drove that point home with devastating force. Japan is one of the most seismically prepared nations on Earth. They have the most advanced earthquake early warning system ever built. Strict building codes, regular drills, seawalls along vulnerable coastlines. They were as ready as any society has ever been. But the earthquake that struck on March 11, 2011, was bigger than anything the models had predicted for that particular fault. Magnitude 9.1, the fourth most powerful earthquake ever recorded by instruments. The seismic models had assumed that the fault segment couldn't produce anything larger than about 8.0. They were wrong. The earthquake shifted the main island of Honshu about 8 feet to the east and moved the Earth's axis by several inches. It generated a tsunami that topped 40 meters, over 130 feet, in some locations, overtopping seawalls that had been designed for much smaller waves. Nearly 20,000 people died. The Fukushima Daiichi nuclear plant, which had been built to withstand earthquakes and tsunamis, was overwhelmed. The seawalls were high enough for the scenarios the engineers had planned for. They weren't high enough for the scenario that actually happened. There's a hard lesson in that, and it applies far beyond seismology. Engineering is the art of designing for the world as it actually is, not as you assume it to be. And the world, this planet, keeps surprising us. The forces operating beneath our feet are so vast, so powerful, and in some ways so poorly understood, that humility isn't just a virtue in the geosciences, it's a survival strategy. But earthquakes and plate tectonics, as dramatic as they are only part of what the Earth's churning interior produces. There's another consequence, another gift from the liquid iron core spinning thousands of miles beneath your feet, and it's something so fundamental to life on this planet that without it, the surface of the Earth would probably look a lot like Mars, barren, irradiated, stripped of its atmosphere, and utterly lifeless. It's the Earth's magnetic field, and the story of how it works, how we discovered it, and what it does for us, is one of the most fascinating and most confusing things about this planet. People have known about Earth's magnetic field for centuries, of course. The Chinese were using magnetic compasses for navigation by the 11th century, and possibly earlier. The observation that a magnetized needle, floating freely, always points roughly toward the north was one of the most practical and important discoveries in the history of exploration. But knowing that the Earth has a magnetic field and understanding where it comes from are two very different things, and the answer turns out to be genuinely strange. In 1600, William Gilbert, physician to Queen Elizabeth I, published a book called De Magnete, On the Magnet, in which he argued that the Earth itself was a giant magnet. He made a sphere of magnetite, which he called a terrella, a little Earth, and showed that a compass needle near the terrella behaved the same way a compass behaves on the Earth's surface. It was a brilliant insight, and it was correct in the sense that the Earth does behave as if it has a giant bar magnet buried inside it, roughly aligned with the rotational axis. But it raised an obvious question. What makes the Earth magnetic? Is there actually a permanent magnet at the center? The answer is no, and here's why. The interior of the Earth is far too hot for any permanent magnet to work. Every magnetic material has what's called a Curie temperature, the temperature above which it loses its magnetism. For iron, that's about 1,418 degrees Fahrenheit. The Earth's core is thousands of degrees hotter than that. Any permanent magnetism would be erased. The iron in the core is too hot to be a permanent magnet. So where does the magnetic field come from? The answer is the geodynamo, one of the most remarkable natural phenomena in the universe. Here's the basic idea. The Earth's outer core is made of liquid iron, and it's in constant motion, driven by convection, hot metal rising, cooler metal sinking, and also by the Earth's rotation, which introduces twisting forces through the Coriolis effect. This flowing, electrically conductive liquid metal acts like a self-sustaining electromagnetic generator. Moving conductive fluid in the presence of even a very weak magnetic field generates electric currents. Those electric currents, in turn, generate their own magnetic field. And that generated field reinforces the original field, which drives more currents, which generate more field. It's a feedback loop, a self-exciting dynamo. The Earth's magnetic field isn't produced by a permanent magnet. It's produced by the motion of liquid iron, continuously regenerated by the planet's own internal heat and rotation. Now, this is one of those ideas that's deceptively simple in outline, but fiendishly complex in detail. The mathematics of magnetohydrodynamics. Yes, that's a real word, and it's exactly what it sounds like. The dynamics of electrically conducting fluids in magnetic fields is some of the hardest math in all of physics. Simulating the geodynamo on a computer requires enormous computational power, and even the best models can only approximate what's happening. The flow patterns in the outer core are chaotic and turbulent, with complex interactions between convection, rotation, and magnetic forces. It's not a neat, tidy system. It's messy, dynamic, and constantly evolving. And here's proof of that messiness. The magnetic field reverses. Every so often, on geological timescales, the north and south magnetic poles swap. What was magnetic north becomes magnetic south, and vice versa. This has happened hundreds of times in the Earth's history. The reversals are irregular. Sometimes a polarity persists for millions of years, sometimes for just tens of thousands. The most recent reversal happened about 780,000 years ago, which is called the Brunhes-Matuyama reversal. We know all this because of those magnetic stripes on the ocean floor we talked about. The record of polarity is stamped into the cooling rock at mid-ocean ridges, creating a timeline of reversals that stretches back hundreds of millions of years. Nobody fully understands what triggers a reversal. Simulations suggest that it's a consequence of the chaotic dynamics of the outer core. The flow patterns occasionally reorganize in a way that flips the polarity. During a reversal, which can take anywhere from 100 to a few thousand years, the field becomes weak and complex, with multiple poles and irregular geometry. It doesn't just cleanly flip. It gets confused for a while, and then it settles into the new orientation. And during that confused period, the field is weaker, which means less protection from the solar wind and cosmic radiation. Whether that's dangerous for life at the surface is debated. Some researchers have suggested links between reversals and extinction events, but the evidence is inconclusive. The last reversal happened long before modern humans existed, so we have no historical experience of one. But here's why the magnetic field matters so much. It's not just useful for compass navigation. It's a shield. The sun is constantly blasting the solar system with a stream of charged particles, protons and electrons, called the solar wind. This stream moves at about 1,000,000 miles per hour, and it carries with it the sun's own magnetic field. When that solar wind hits the Earth, the magnetic field deflects it, channeling the charged particles around the planet, like water flowing around a rock in a stream. This creates a region of space called the magnetosphere, a magnetic bubble surrounding the Earth that extends tens of thousands of miles into space on the sunward side and stretches into a long tail on the night side. Without this shield, the solar wind would gradually strip away the Earth's atmosphere, and we have a perfect case study to prove it: Mars. Mars once had a thicker atmosphere, liquid water on its surface, and possibly conditions suitable for life. But Mars is smaller than Earth, and it cooled faster. Its core solidified, the dynamo shut down, and the magnetic field collapsed. Without that magnetic protection, the solar wind has been slowly eroding Mars's atmosphere for billions of years. Today, Mars has an atmosphere less than 1% as dense as Earth's. Its surface is bathed in radiation. Any liquid water is long gone. Mars is what happens when a rocky planet loses its magnetic field. And here's the beautiful consequence of Earth's magnetic field that most people have actually seen, or at least heard of: the auroras, the northern lights, the southern lights. Even though the magnetosphere deflects most of the solar wind, some charged particles get funneled along the magnetic field lines toward the poles, where the field lines converge and dip down toward the surface. When those high-energy particles collide with atoms and molecules in the upper atmosphere, they excite them, bump their electrons to higher energy levels, and when those electrons drop back down, they emit light. Green from oxygen at lower altitudes, red from oxygen higher up, blue and purple from nitrogen. It's one of the most beautiful natural phenomena on Earth, and it's caused by the interaction between an electrically conductive iron alloy churning thousands of miles below your feet and a stream of charged particles blasted from the surface of a star 93 million miles away. That's the kind of thing that makes you appreciate just how connected everything is. So the inner workings of the Earth give us plate tectonics, earthquakes, volcanoes, the magnetic field, and the auroras. That's a lot for a ball of rock and metal. But there's another defining feature of this planet that doesn't come from the inside, or at least not entirely. And it's something so basic, so ubiquitous, so deeply woven into our everyday experience that we barely think about it: water. Earth is the water planet. About 71% of the surface is covered by ocean, and those oceans are deep. The average depth of the ocean is about 12,100 feet, roughly 2.33 miles. The deepest point, the Challenger Deep in the Mariana Trench, plunges nearly 36,000 feet, almost 7 miles down. If you placed Mount Everest at the bottom of the Mariana Trench, its peak would still be more than a mile underwater. There's water in the atmosphere as vapor, in glaciers as ice, in rivers and lakes and underground aquifers. The total amount of water on and in the Earth is about 332.5 million cubic miles. And the question of where all that water came from is one of the most confusing and most debated topics in planetary science. The simplest version of the question is this: the early Earth was a hellscape. When the planet first formed, about 4.54 billion years ago, it was incredibly hot, partly from the energy of all those colliding rocky bodies aggregating together, partly from radioactive decay, and partly from a cataclysmic event that we need to talk about in a moment. The surface was molten. Any water that might have been present would have been vaporized and likely blasted away into space by the intense solar wind from the young sun, which was far more active and violent in its early years. So where did the water come from later? But before we get to the water, we need to talk about the moon, because the moon's origin is intimately connected to the early history of the Earth, and it's one of the most dramatic stories in all of planetary science. You look up at the moon, assuming you're ever awake when it's visible, and it seems like such a calm, peaceful, permanent fixture of the sky. It's always been there, right? Well, no. It hasn't always been there. And the way it got there is almost unbelievably violent. The leading theory for the formation of the moon is called the giant impact hypothesis, and it goes like this. About 4.5 billion years ago, when the Earth was still very young, maybe 50 to 100 million years after it first formed, a Mars-sized body slammed into it. Not a glancing blow, a massive, catastrophic collision. This hypothetical impactor is sometimes called Theia, after the Greek Titan, who was the mother of Selene, the moon goddess. The impact would have been unimaginably energetic. A substantial portion of both the Earth and Theia would have been vaporized. The collision would have blasted enormous amounts of debris into orbit around the Earth, a disk of superheated rock and vapor, a ring of destruction circling the shattered planet. And from that ring of debris, over a relatively short period, maybe just a few centuries, the moon coalesced. Now, the giant impact hypothesis isn't the only theory that's been proposed. Earlier ideas included the fission hypothesis, that the moon spun off from a rapidly rotating early Earth, like a blob of clay flying off a potter's wheel. There was the capture hypothesis, that the moon formed elsewhere in the solar system and was captured by Earth's gravity as it passed by. And there was the co-accretion hypothesis, that the Earth and moon formed side by side from the same disk of material. Each of these has problems. Fission can't explain the moon's orbital dynamics. Capture is gravitationally unlikely, without some mechanism to slow the moon down enough to be caught. And co-accretion can't easily explain why the moon has such a small iron core compared to Earth. The giant impact hypothesis solves all of these problems, and it's supported by several lines of evidence. There are several lines of evidence supporting this theory. The moon's composition is remarkably similar to the Earth's mantle. It has a very similar mix of oxygen isotopes, which is like a chemical fingerprint. If the moon had formed somewhere else in the solar system and been captured by Earth's gravity, you'd expect a very different composition. The similarity suggests the moon was made from Earth material. The moon also has a tiny iron core relative to its size, which makes sense if it formed mostly from mantle material blasted off the Earth's outer layers, rather than from a complete planet with its own proportional core. And the angular momentum of the Earth-Moon system, the total amount of rotational motion, is consistent with a giant impact. But the moon isn't just a pretty thing to look at. It does two things for the Earth that are profoundly important, and without them, this planet would be a very different place. The first is tides. The moon's gravity pulls on the Earth, And because the moon is much closer to one side of the Earth than the other, that pull is slightly stronger on the near side and slightly weaker on the far side. This differential pull, the tidal force, stretches the Earth slightly along the line connecting it to the moon, creating two bulges of water on opposite sides of the planet. One bulge faces the moon, pulled toward it by the stronger gravitational attraction. The other bulge is on the far side, where the weaker lunar gravity allows the water to bulge outward, or more precisely, the Earth beneath it is being pulled away from the water more strongly than the water itself is being pulled. As the Earth rotates beneath these two bulges, any given coastline passes through both of them each day, which is why most coastal locations experience 2 high tides and 2 low tides every 24 hours and 50 minutes. The extra 50 minutes accounting for the moon's own motion around the Earth. Now, here's something that might surprise you. Tides aren't just about water levels at the beach. The tidal interaction between the Earth and moon is gradually slowing the Earth's rotation. The tidal bulges are slightly ahead of the moon because the Earth rotates faster than the moon orbits, and the gravitational interaction between the moon and these ahead-positioned bulges acts as a brake on the Earth's spin. The days are getting longer, by about 2-3 milliseconds per century. That's not much now, but over geological time it adds up. When the Earth first formed, a day was probably only about 6 hours long. The moon was also much closer, perhaps only about 15,000 miles away, compared to its current distance of about 239,000 miles. It would have looked enormous in the sky, and the tides would have been apocalyptically powerful. The second crucial thing the moon does is stabilize the Earth's axial tilt. Remember how we talked about the tilt being about 23.4 degrees? That tilt gives us seasons, and it varies slightly over tens of thousands of years as part of the Milankovitch cycles. But without the moon's gravitational influence, the tilt wouldn't just vary slightly. It would swing wildly, potentially from nearly 0 degrees to over 50 degrees, chaotically, over timescales of millions of years. Mars, which has no large moon, actually experiences this kind of chaotic tilt variation. Computer simulations show that Mars's axial tilt has probably wandered between about 15 and 45 degrees over the last few billion years. If Earth's tilt swung that wildly, the climate consequences would be extreme. Seasons would go from barely existing to brutal and back again, with polar regions sometimes facing the sun directly and equatorial regions plunging into darkness for months. The stability provided by the moon's gravitational pull on Earth's equatorial bulge keeps the tilt variations small and slow, giving the climate a regularity that has been important for the evolution of complex life. This impact would have essentially reset the Earth's surface. Any early crust, any early atmosphere, any early water would have been destroyed. The Earth, after the impact, was a ball of magma, slowly cooling, slowly building a new crust. And as it cooled, something had to supply the water that would eventually fill the oceans. There are 2 main candidates. The first is outgassing, volcanic eruptions releasing water vapor that had been trapped in the minerals of the Earth's interior. When rock melts and rises to the surface, the water bound up in its crystal structure is released as steam. Over hundreds of millions of years of volcanic activity, enormous quantities of water vapor could have been released into the atmosphere, where it would eventually cool, condense, and rain down. Imagine rain falling for millions of years, slowly filling the ocean basins. The water was inside the Earth all along, locked up in the mantle, and volcanoes set it free. The second candidate is delivery from space, specifically from asteroids and comets. During a period called the Late Heavy Bombardment, roughly 4.1 to 3.8 billion years ago, the inner solar system was pummeled by a barrage of asteroids. Many of these were carbonaceous chondrites, a type of asteroid that contains significant amounts of water bound up in hydrated minerals. If enough of these water-rich asteroids hit the early Earth, they could have delivered a substantial portion of the oceans. Comets, which are essentially dirty snowballs, mixtures of ice and rock, were also once considered a major source, but recent measurements of the water in several comets have shown that their hydrogen isotope ratios don't quite match Earth's oceans. The water in most comets has a different flavor of hydrogen, more deuterium, the heavy isotope, than Earth's ocean water. Asteroids, on the other hand, are a much closer match. So the current thinking is that most of Earth's water probably came from a combination of outgassing from the interior and delivery by asteroids, with comets playing a smaller role. However, and this is the kind of thing that keeps planetary scientists up at night, recent research has complicated the picture further. Some models suggest that the Earth may have retained more of its original water through the giant impact than previously thought, that not all of it was blasted away. Other work has found that the solar nebula itself, the cloud of gas and dust from which the entire solar system formed, could have contributed hydrogen to the forming Earth, which then combined with oxygen to make water. The honest answer is that we're still not entirely sure where Earth's water came from. We have good candidates, good evidence for several mechanisms, and the truth is probably a combination. But pinning down the exact proportions remains an active area of research. What we do know is that once the water was here, it transformed the planet. Water is, in many ways, the single most important substance on Earth, not just for life, but for geology. Water erodes rock, creating valleys and canyons, and shaping landscapes over millions of years. Water carries dissolved minerals from the continents into the oceans, where they precipitate out and form new sedimentary rocks. Water lubricates tectonic faults, influencing where and how earthquakes occur. Water in the mantle lowers the melting point of rock, enabling the partial melting that produces magma and drives volcanism. Without water, plate tectonics might not even work the way it does. Some geologists argue that water is essential for subduction, because it weakens the oceanic crust enough for it to bend and dive into the mantle. Earth without water wouldn't just be a dry version of itself. It would be a fundamentally different planet, and the oceans, once they formed, set up one of the most important systems on Earth, the global ocean circulation. You've probably heard of the Gulf Stream, the warm current that flows from the Gulf of Mexico northeast across the Atlantic, bringing warmth to Western Europe. London is at about the same latitude as Labrador in Canada, but London's winters are far milder, because the Gulf Stream delivers enormous amounts of heat from the tropics. But the Gulf Stream is just one piece of a much larger pattern. The ocean has a global conveyor belt of circulation called thermohaline circulation, thermo for temperature, haline for salinity, because both heat and salt content drive the flow. Here's the basic idea. In the North Atlantic, near Greenland and Iceland, cold winds cool the surface water. As the water cools, it gets denser. At the same time, when sea ice forms, it rejects salt. The ice itself is mostly fresh water, so the remaining liquid water gets saltier, and therefore denser. This cold, salty water is so dense that it sinks, plunging from the surface to the deep ocean in a process called deep water formation. It then flows slowly along the ocean floor, all the way southward through the Atlantic, around Antarctica, and into the Indian and Pacific Oceans. Eventually, thousands of years later, it warms, rises back to the surface in other parts of the world, and makes its way back to the North Atlantic to start the cycle again. One complete circuit takes roughly 1,000 years. The water that's currently sinking near Greenland won't return to the surface until long after everyone alive today is gone. It's a slow, patient system, moving vast quantities of water at the pace of a few centimeters per second, but the volumes involved are staggering. The Atlantic meridional overturning circulation alone moves roughly 20 million cubic meters of water per second, about 100 times the flow of the Amazon River. This circulation is profoundly important for the Earth's climate. It redistributes heat around the planet, moving warm water from the tropics toward the poles, and cold water from the poles toward the equator. It also moves nutrients, dissolved gases, and carbon dioxide through the deep ocean. If this conveyor belt were to slow down or shut off, which has happened in the geological past, the consequences for global climate would be dramatic. During the last ice age, there's evidence that the thermohaline circulation was significantly weaker, and some researchers think that periodic disruptions of the circulation may have triggered abrupt climate shifts, sudden cooling events that happened within decades, not centuries. And that brings us to one of the most fascinating and most confusing questions about Earth. Why does the climate change? Not human-caused climate change, which is real and well understood and happening right now. I'm talking about the natural cycles of warming and cooling that have characterized the Earth's climate for billions of years. Ice ages and warm periods, snowball Earths and tropical poles. Why does the planet's climate swing between such extremes? Let's start with ice ages, because they're the most recent and best understood natural climate cycles. For the past 2.5 million years or so, a period called the Quaternary, the Earth has been in an ice age. That might sound wrong, because we're not buried under glaciers right now. But in geological terms, an ice age just means a period when there are permanent ice sheets at the poles. We're in an ice age. We're in a warm period within that ice age, an interglacial, but the ice sheets of Greenland and Antarctica are still there. The last glacial maximum, when ice sheets covered much of North America and Northern Europe, was only about 20,000 years ago. That's yesterday in geological time. Chicago was under a mile of ice. The cycles of glaciation and interglaciation within an ice age are driven primarily by variations in Earth's orbit around the Sun. These are called Milankovitch cycles, after the Serbian engineer and mathematician Milutin Milanković, who worked out the theory in the 1920s and 1930s. And the idea is beautiful in its simplicity, even if the details get complicated. The Earth's orbit isn't a perfect circle. It's an ellipse, and the shape of that ellipse changes over time, getting more circular, and then more elongated on a cycle of roughly 100,000 years. This is called eccentricity. When the orbit is more elongated, the difference between the closest approach to the Sun and the farthest point is greater, which means more variation in the amount of solar energy the Earth receives over the course of a year. Then there's the tilt of the Earth's axis. Right now, the axis is tilted about 23.4 degrees from vertical. That's what gives us seasons, because it means the northern hemisphere is tilted toward the Sun for half the year and away from it for the other half. But this tilt angle varies between about 22.1 and 24.5 degrees on a cycle of roughly 41,000 years. A greater tilt means more extreme seasons, hotter summers and colder winters. A smaller tilt means milder seasons. And finally, there's precession, the slow wobble of the Earth's axis, like a spinning top that's winding down. This wobble changes which hemisphere is tilted toward the Sun at the closest point in Earth's orbit, on a cycle of roughly 26,000 years. Right now, the northern hemisphere's summer coincides with Earth being relatively far from the Sun, which makes northern hemisphere summers slightly milder. In about 13,000 years, it'll be the opposite. None of these orbital variations changes the total amount of solar energy Earth receives very much. The key insight, and this is what makes Milankovich's theory so clever, is that what matters most isn't total energy, but the distribution of energy across seasons and latitudes. Specifically, the critical factor for starting or ending a glaciation is the amount of solar energy hitting the high latitudes of the northern hemisphere during summer. If northern summers are cool enough that winter snow doesn't fully melt, it accumulates year after year. The white snow reflects sunlight back into space, cooling the region further, allowing more snow to survive the next summer. It's a feedback loop, a snowball effect, almost literally. Over thousands of years, those surviving snow patches grow into massive ice sheets, miles thick, covering entire continents. And Milankovitch worked all of this out, painstakingly, by hand, calculating the orbital variations and the resulting changes in solar heating at different latitudes for hundreds of thousands of years. This was decades before computers. He did it with tables of numbers and long, tedious arithmetic, a monumental feat of calculation. And when deep-sea sediment cores and ice cores eventually provided a detailed record of past climate, the cycles matched his predictions remarkably well. The ice ages dance to the rhythm of Earth's orbit, but Milankovitch cycles are just the pacemaker. They set the timing. The full story involves feedback mechanisms that amplify those subtle orbital nudges into dramatic climate shifts. Carbon dioxide plays a central role. When ice sheets grow, the oceans absorb more CO2, pulling it out of the atmosphere and cooling the planet further. When ice sheets retreat, the oceans release CO2, warming the planet further. It's a feedback loop. The orbital variations trigger an initial warming or cooling, and the carbon cycle amplifies it. The temperature changes we see in the ice core record are much larger than what the orbital variations alone could produce. The orbit pulls the trigger, but the carbon cycle fires the bullet. And this connects to something even more dramatic. If you go further back in Earth's history, you find climate swings that make the Quaternary ice ages look gentle. Around 700 million years ago, during the Cryogenian period, there's evidence that the entire planet, or very nearly the entire planet, froze over. Ice sheets reached the equator. The oceans may have been covered with ice hundreds of meters thick. This is the snowball Earth hypothesis, and it's one of the most extreme events in the planet's history. The evidence comes from glacial deposits found at locations that were near the equator at the time, based on paleomagnetic data. Finding glacial rubble in the tropics is hard to explain any other way. How did the Earth escape from a snowball? Volcanoes. Even with the surface frozen, volcanic activity continued, pumping carbon dioxide into the atmosphere. Normally, CO2 is removed from the atmosphere by chemical weathering. It reacts with exposed rock and gets washed into the ocean as carbonate. But with the surface frozen, there was no exposed rock and no liquid water for weathering. So CO2 just accumulated for millions of years, until the greenhouse effect became so intense that the ice couldn't maintain itself. And then, when the thaw began, it happened fast. Geological fast, anyway. The flip from snowball to greenhouse was probably dramatic and violent, with extreme storms, rapid sea level changes, and wild temperature swings. And here's the thing. The Snowball Earth episodes may have been crucial for the evolution of complex life. Just after the snowball periods ended, during the Ediacaran period, the first large, complex multicellular organisms appear in the fossil record. Some scientists think the extreme environmental stress of the snowball selected for organisms that could survive challenging conditions, and the nutrient-rich meltwater that followed the thaw provided a burst of opportunity. Life didn't just survive the snowball. It may have been catalyzed by it. But to really understand why Earth's atmosphere and climate behave the way they do, we need to go even further back and talk about the atmosphere itself, where it came from, and how it was transformed into something breathable. Because the air you're breathing right now, this comfortable mix of about 78% nitrogen and 21% oxygen, is not what Earth started with, not even close. And the story of how oxygen got into the atmosphere is, arguably, the most important event in the history of life on Earth. And it was caused not by any geological process, not by any cosmic event, but by tiny, humble, single-celled organisms that stumbled onto a chemical trick so powerful that it literally rusted the oceans and poisoned most of the existing life on the planet. The early atmosphere of the Earth, in the first billion years or so, was nothing like today's. It was rich in nitrogen, carbon dioxide, water vapor, and probably methane and ammonia, but it contained essentially no free oxygen, no O2. If you could go back to the early Earth and take a breath, you'd suffocate. The air was reducing, not oxidizing. Iron dissolved freely in the oceans without rusting. The chemistry of the surface was fundamentally different from what we know today. And then, sometime around 2.4 billion years ago, give or take, something changed. Oxygen levels in the atmosphere spiked, not gradually, not gently, but in what geologists call the Great Oxidation Event. And the cause was cyanobacteria, photosynthetic microorganisms, sometimes informally called blue-green algae, though they're not actually algae. Cyanobacteria had evolved a new form of photosynthesis. An earlier version of photosynthesis already existed, but it didn't produce oxygen. Cyanobacteria developed a version that split water molecules, H2O, using sunlight as the energy source, and released the oxygen atoms as a waste product. They were, essentially, the first organisms on Earth to breathe out oxygen, and they were wildly successful. Think about what happened next. These tiny creatures, floating in the sunlit upper layers of ancient oceans, were pumping out oxygen as a metabolic byproduct. At first, the oxygen didn't accumulate in the atmosphere. It was absorbed by chemical reactions. It oxidized dissolved iron in the oceans, producing iron oxide, which sank to the ocean floor. This is actually where banded iron formations come from, those beautiful striped rocks of alternating iron-rich and iron-poor layers that are found all over the world in rocks of this age. They're literally the rust of an ocean being poisoned by oxygen. They're a geological record of the most consequential pollution event in the history of life. Eventually, the oxygen sinks were overwhelmed. There was only so much dissolved iron to oxidize, only so much reduced rock to react with. And once those sinks were saturated, the oxygen began to accumulate in the atmosphere. And for most of the existing life on Earth, this was an absolute catastrophe. Most organisms at the time were anaerobic. They thrived in oxygen-free environments and were poisoned by oxygen, which is, from a chemical perspective, a highly reactive and corrosive gas. The Great Oxidation Event was, for these organisms, a mass extinction, a global poisoning, the worst pollution disaster in the history of the planet, caused by organisms that had no idea what they were doing. But for the organisms that could tolerate oxygen, or better yet, could use it, and eventually, evolution would produce organisms that could harness oxygen's reactivity for a much more efficient form of metabolism, aerobic respiration. The Great Oxidation Event opened up entirely new possibilities. Oxygen-based metabolism produces roughly 18 times more energy per glucose molecule than anaerobic metabolism. That extra energy budget eventually made possible larger, more complex, more active organisms, including, eventually, you. And oxygen did something else that was crucial. High in the atmosphere, ultraviolet radiation from the sun splits oxygen molecules, O2, and the resulting oxygen atoms recombine to form ozone, O3. This ozone layer absorbs most of the sun's harmful ultraviolet radiation, shielding the surface below. Before the ozone layer formed, the land surface was bathed in sterilizing UV radiation. Life was confined to the oceans, where water provided protection. Once the ozone layer was established, life could colonize land, plants, then animals, then everything that followed. The ozone layer, this thin, fragile band of triatomic oxygen high in the stratosphere, is the reason forests and grasslands and cities exist on dry land instead of everything living underwater. So the air you're breathing, this invisible mixture of gases that feels so natural and permanent, is actually a byproduct of biological activity. It was manufactured by life itself, over billions of years of photosynthesis. The atmosphere is not just a physical feature of the planet, it's a biological artifact, and it's connected, through the greenhouse effect, to the planet's temperature in a way that's both simple in principle and enormously complex in practice. The greenhouse effect itself is straightforward, and it's not a bad thing. It's essential. Without any greenhouse effect at all, the average temperature of the Earth's surface would be about 0 degrees Fahrenheit, well below freezing. The oceans would be ice. The planet would be uninhabitable. What the greenhouse effect does is this. The sun's energy arrives at Earth mostly as visible light. The surface absorbs that light and warms up. The warm surface then radiates energy back upward as infrared radiation, heat. But certain gases in the atmosphere, carbon dioxide, water vapor, methane, nitrous oxide, and a few others, are transparent to visible light but absorb infrared radiation. They trap some of the outgoing heat and re-radiate it in all directions, including back toward the surface. This warms the surface more than sunlight alone would. It's like putting a blanket over the planet. The blanket doesn't generate heat. It just slows down the rate at which heat escapes. And the thicker the blanket, the more greenhouse gases in the atmosphere, the warmer the surface gets. And since we're talking about sunlight and the atmosphere, let's take a moment for something that seems simple, but is actually kind of wonderful. Why is the sky blue? You've probably been told it's because the atmosphere scatters blue light, and that's true, but it's worth understanding what that actually means. Sunlight is white light, a mixture of all visible wavelengths, all colors. When that light enters the atmosphere, it collides with the tiny molecules of nitrogen and oxygen that make up most of the air. And here's the key physics. These molecules scatter shorter wavelengths of light, blue and violet, much more efficiently than longer wavelengths, red and orange. This is called Rayleigh scattering, after the British physicist Lord Rayleigh, who worked out the math in the 1870s. The scattering goes as the fourth power of the frequency, which means violet light is scattered even more than blue. So why isn't the sky violet? 2 reasons. First, the sun emits slightly more blue light than violet. And second, your eyes are more sensitive to blue than to violet. So the sky looks blue, even though violet is being scattered more. It's a collaboration between the sun's spectrum and your biology. And at sunset, when the sun is low on the horizon, its light has to pass through a much thicker slice of atmosphere to reach your eyes. By the time it arrives, most of the blue light has been scattered away, sideways, upward, in every direction except straight at you. What's left is the longer wavelengths, red, orange, gold. That's why sunsets are red. The same physics that makes the daytime sky blue makes the evening sky glow with warm colors. And if there are clouds or dust particles in the atmosphere, they scatter and reflect those warm colors even more, which is why the most spectacular sunsets often happen after volcanic eruptions or on dusty, hazy days. And while we're on the subject of sunlight, let's quickly clear up one of the most common misconceptions about Earth. Why do we have seasons? Most people think it's because the Earth is closer to the sun in summer and farther away in winter. That's wrong. In fact, in the northern hemisphere, summer happens when the Earth is actually slightly farther from the sun. Earth is at its closest to the sun, a point called perihelion, in early January, right in the middle of the northern hemisphere's winter. The difference in distance between perihelion and aphelion, the farthest point, is only about 3%, and it has almost no effect on the seasons. Seasons are caused by the tilt of the Earth's axis. When the northern hemisphere is tilted toward the sun, sunlight hits the northern latitudes at a more direct angle, more concentrated, more intense, and the days are longer, which means more total hours of heating. That's summer. 6 months later, the northern hemisphere is tilted away from the sun. The sunlight arrives at a more oblique angle, spreading the same energy over a larger area, and the days are shorter. That's winter. The southern hemisphere experiences the opposite pattern at the same time. It's all geometry, the angle at which sunlight hits the surface, and how many hours it shines. The natural greenhouse effect raises Earth's average surface temperature from about 0 Fahrenheit to about 59 degrees Fahrenheit. That's the difference between a frozen wasteland and the lush, habitable world we know. The problem, of course, is when you start adding more greenhouse gases beyond what the natural system would produce, thickening the blanket faster than the planet's feedback systems can adjust. But that's a modern story. And tonight, we're focused on the deeper history, the billions of years of processes that made this planet what it is. And one of the most dramatic chapters in that history involves mass extinctions, moments when a significant fraction of all species on Earth disappeared in a geologically short period. There have been 5 major mass extinctions in the last 540 million years, and each one reshaped the trajectory of life on this planet. The end Ordovician, about 445 million years ago, killed roughly 85% of marine species, probably caused by a sudden glaciation as the supercontinent Gondwana drifted over the South Pole. The late Devonian, around 375 million years ago, wiped out about 75% of species over a prolonged period, possibly related to the spread of land plants whose deep roots accelerated rock weathering, which pulled carbon dioxide from the atmosphere and cooled the planet. The end Permian, 252 million years ago, was the worst of all, the Great Dying, killing roughly 96% of all marine species and 70% of terrestrial vertebrate species. The primary culprit appears to have been massive volcanic eruptions in what is now Siberia, the Siberian Traps, which released staggering amounts of carbon dioxide and sulfur dioxide over tens of thousands of years, triggering runaway warming, ocean acidification, and ocean anoxia. It nearly sterilized the planet. Life took 10 million years to fully recover, and the end Triassic, about 201 million years ago, killed about 75% of species, again linked to massive volcanism. This time, the Central Atlantic Magmatic Province. But the one that captures the imagination most, the one that's seared into popular culture, is the one that killed the dinosaurs, the end Cretaceous extinction, 66 million years ago. And the story of how we figured out what caused it is one of the great detective stories in the history of science. For a long time, the extinction of the dinosaurs was a mystery. They'd been dominant for over 160 million years, the most successful large animals the planet had ever seen. And then, at the boundary between the Cretaceous and Paleogene periods, they were gone, along with about 75% of all species on Earth. The fossil record shows a sharp, sudden disappearance, not a gradual decline over millions of years, but a catastrophic event. What could possibly wipe out 3/4 of all living species in what appears to be an instant of geological time? The answer came from an unlikely source, a physicist, not a paleontologist. In the late 1970s, Luis Alvarez, a Nobel Prize-winning physicist at Berkeley, and his son Walter Alvarez, a geologist, were studying a thin layer of clay in the geological record that corresponded exactly to the Cretaceous-Paleogene boundary. This clay layer is found all over the world, and it marks the moment of the extinction. The Alvarezes analyzed the composition of this clay and found something astonishing. It was enriched in iridium, a rare element on the Earth's surface, but common in asteroids and meteorites, by a factor of about 30 times the normal background level. There was too much iridium for any terrestrial source. It had to have come from space. Luis Alvarez was not a typical geologist. He was a physicist who had worked on the Manhattan Project and had won the Nobel Prize for his work on particle physics. He brought a physicist's instinct for measurement and evidence to a geological problem, and the combination was devastatingly effective. His son Walter, the geologist, had found the clay layer and noticed it was unusual. Luis looked at the iridium data and immediately recognized its cosmic implications. Together, in 1980, the Alvarezes published their hypothesis. An asteroid, roughly 6 miles in diameter, about the size of Mount Everest, had struck the Earth 66 million years ago. The impact would have released energy equivalent to billions of nuclear weapons. The explosion would have set the surrounding area on fire, sent a massive tsunami radiating outward, and blasted enormous quantities of dust and debris into the atmosphere, including the iridium-rich material that settled around the world as that thin clay layer. The dust cloud would have blocked sunlight for months, perhaps years, plunging the planet into a prolonged winter. Photosynthesis would have collapsed. Food chains would have disintegrated. The darkness and cold would have lasted long enough to kill anything that couldn't find shelter, find alternative food sources, or simply endure. Think about the day itself for a moment. An asteroid 6 miles wide, traveling at roughly 45,000 miles per hour, slams into shallow tropical seas. The impact vaporizes both the asteroid and a massive volume of rock and seawater instantly. A fireball expands outward, incinerating everything within a radius of hundreds of miles. The shockwave flattens forests across North America. Earthquakes, magnitude 10 or greater, far beyond anything in human experience, ripple around the planet. Tsunamis hundreds of feet high radiate outward across the Atlantic and the Gulf of Mexico, scouring coastlines thousands of miles away. And then the debris, trillions of tons of pulverized rock, launched high above the atmosphere, begins to rain back down, heating the upper atmosphere through friction until the sky itself glows red-hot. Some models suggest the thermal radiation from the re-entering debris was intense enough to ignite wildfires across entire continents. And then came the long darkness. The dust and sulfur aerosols blocked sunlight for months, possibly years. Global temperatures plunged. Photosynthesis shut down. The base of the food chain collapsed. It was, by any reasonable definition, the worst single day in the history of complex life on Earth. The hypothesis was controversial at first. Many paleontologists were skeptical. Some argued that the extinction had been caused by volcanic activity, specifically, the massive eruptions that created the Deccan Traps in India, enormous floods of basalt that did indeed occur around the same time and would have released huge amounts of sulfur dioxide and carbon dioxide into the atmosphere. There was a genuine scientific debate, and it lasted for years. And then, in 1991, the smoking gun was found. A group of researchers identified a massive impact crater buried beneath the Yucatan Peninsula in Mexico, near the town of Chicxulub. The crater was about 110 miles in diameter, enormous, and radiometric dating showed it was exactly the right age, 66 million years. The physical evidence was overwhelming. Shocked quartz, mineral grains deformed by the incredible pressures of an impact, pressures that no volcanic eruption can produce, was found in the boundary clay worldwide. Tiny glass spherules, droplets of rock melted by the impact and then solidified as they rained back down, were found across the Americas. The case was closed. An asteroid hit the Earth, and it ended the age of dinosaurs. But here's what's worth lingering on. The asteroid didn't just destroy. It also created opportunity. The extinction of the dinosaurs, and of so many other species, opened up ecological niches that had been occupied for over 100 million years, and the organisms that survived, including small, burrowing, nocturnal mammals, diversified rapidly into those empty niches. Within 10 million years of the impact, mammals had evolved into a stunning array of forms, from tiny insectivores to large herbivores to the first primates. Our own lineage traces directly back to those small, frightened creatures that somehow survived the worst day in the history of complex life. If that asteroid had missed, if it had arrived 6 hours earlier or later, hitting open ocean instead of the shallow, sulfate-rich seabed of the Yucatan, which made the impact especially deadly, the dinosaurs might still be here, and we almost certainly would not be. The entire trajectory of life on Earth, the fact that you are lying here right now, capable of thinking about all of this, hinges on a rock from space, hitting the right place at the right time, 66 million years ago. And this is what I keep coming back to when I think about Earth. Every feature of this planet, every mountain, every ocean, every breath of air, every grain of sand, has a story. And the stories are all connected. The heat from radioactive decay in the interior drives convection in the mantle, which moves the plates, which builds mountains and opens oceans, which creates earthquakes and volcanoes. The churning liquid iron in the outer core generates the magnetic field that shields the atmosphere from the solar wind. The atmosphere, manufactured by billions of years of photosynthesis, traps just enough heat to keep the oceans liquid. The oceans distribute that heat around the planet through thermohaline circulation. The orbit wobbles, the ice advances and retreats, and life adapts and evolves, and is occasionally devastated by rocks from space or poisons from within. It's all one system, one incredibly complex, deeply interconnected, constantly evolving system, and you're part of it, right now. The calcium in your bones was forged in the heart of a dying star, accreted into the dust cloud that became the solar system, incorporated into the rocky planet that coalesced 4.54 billion years ago, cycled through the Earth's crust by plate tectonics, dissolved into ocean water, taken up by organisms, deposited as limestone, uplifted into mountains, eroded by rain, carried down rivers, and eventually eaten by you in some piece of food that you've already forgotten about. The iron in your blood, the iron that carries oxygen to your cells, is the same element that churns in liquid form thousands of miles below you, generating the magnetic field that protects the very atmosphere you're breathing. The oxygen you're inhaling right now was exhaled by a plant, which got it from splitting water molecules using the same photosynthetic trick that cyanobacteria invented 2.5 billion years ago. You are made of this planet, not metaphorically, literally. Every atom in your body has been part of the Earth for billions of years, cycling through rocks and oceans and atmospheres and organisms, over and over and over. You are a temporary arrangement of Earth materials, borrowing atoms that the planet will reclaim when you're done with them. And the planet will keep going, It'll keep spinning, keep churning, keep recycling. The plates will keep drifting. The magnetic field will keep humming. The oceans will keep circulating. New mountains will rise. Old ones will erode away. The sun will keep shining for another 5 billion years, and the Earth will keep orbiting, and the whole magnificent, confusing, improbable system will keep running. And you know what? For all the confusing things about Earth, the invisible forces, the deep time processes, the chaotic systems and catastrophic surprises, the most confusing thing might be the simplest one, that it exists at all, that a cloud of gas and dust collapsed under its own gravity 4.5 billion years ago and produced this. A rocky planet with liquid water and a breathable atmosphere and a magnetic shield and active geology and life. We've looked at thousands of exoplanets now. NASA's Kepler Space Telescope alone confirmed over 2,600, and we haven't found anything quite like it. We've found rocky planets in habitable zones, sure. We've found planets with atmospheres. We've found planets with water vapor in their spectra. But the full package, the magnetic field, the plate tectonics, the liquid water oceans, the oxygen-rich atmosphere, the large stabilizing moon, the protective magnetosphere, the just right distance from a just right star, we haven't found that combination anywhere else. Not yet. That doesn't mean it's not out there. The universe is vast, and our search has barely begun. But as far as we know, right now, this is it. This is the one place in the cosmos where someone can lie in the dark and think about where they are and what it all means. So let that settle in. The ground beneath you, solid as it feels, is a thin crust floating on a sea of slowly flowing rock, powered by a core of liquid metal spinning in the dark. The air around you was manufactured by organisms that lived and died billions of years before anything with a brain existed. The water in your glass fell as rain, flowed through rivers, filtered through rock, and has been recycling through the Earth system since before the first fish swam. Everything around you is ancient and dynamic and interconnected in ways that took centuries of human effort to even begin to understand. And now you know a little more about all of it. About why the ground shakes and the mountains rise, about why the compass points north and the auroras glow, about why the sky is breathable and the oceans are full, about how a man named Wegener was right and died before anyone believed him, and how a woman named Lehman saw what no one else could see, and how a stubborn geochemist named Patterson measured the age of the planet while accidentally discovering that we were poisoning ourselves with lead. These are human stories, ultimately. Stories of curiosity and stubbornness, and brilliant leaps and painful mistakes. The Earth doesn't need us to understand it. It was here long before us, and it'll be here long after. But the fact that we can understand it, that we can lie here in the dark and trace the story of a planet from a cloud of dust to a living world, that's something worth marveling at. So let the planet spin. Let the mantle churn. Let the core hum its magnetic song. You're riding on the surface of something extraordinary, and you have been since the moment you were born, and you always will be. And right now, the Earth is doing what it always does, turning slowly, steadily, carrying you through space at 67,000 miles per hour, and you can't feel a thing, just warmth and stillness, and the quiet pull of gravity holding you gently in place, which is, when you think about it, the Earth's way of saying, "I've got you. Rest now. I'll keep spinning."